In the quiet hours before dawn, when the world rests in darkness and the stars shine their brightest, ancient Persian astronomers would climb to the rooftops of their temples and palaces. They carried with them instruments so precise, calculations so advanced, that modern scientists are still struggling to understand how they achieved such accuracy over 2,000 years ago. Tonight, as you drift into sleep, let me take you on a journey into the forgotten brilliance of Persian astronomy, where the mysteries of the cosmos were unlocked by minds that saw patterns in the heavens that we're only now beginning to rediscover. Welcome to History for Sleep, where tonight we explore the uncovered secrets of ancient Persian astronomy. I'm here to guide you through a world where mathematics and mysticism dance together under starlit skies, where the movement of planets was mapped with breathtaking precision, and where astronomical knowledge was considered so sacred that much of it was deliberately hidden from the world. But here's what makes this story truly extraordinary. While most people believe that advanced astronomy began with the Greeks or emerged during the Islamic Golden Age, the truth is far more fascinating. Deep within the archives of forgotten libraries, scattered across crumbling manuscripts that survived wars and centuries of neglect, lies evidence of astronomical achievements that predate anything we learned in school. The Persians weren't just watching the stars. They were decoding them, predicting eclipses centuries in advance, and calculating the movements of celestial bodies with an accuracy that wouldn't be matched in Europe for another 1,000 years. Tonight, I'll reveal not just what they discovered, but why so much of their knowledge was intentionally concealed. You'll learn about the secret astronomical schools hidden within Zoroastrian fire temples, the coded star charts that could only be read by initiates, and the revolutionary discoveries that were buried because they challenged the very foundations of how ancient civilizations understood time, space, and their place in the universe. As we journey together through these forgotten chapters of human achievement, let the gentle rhythm of this story carry you toward peaceful sleep. Close your eyes and allow yourself to drift back through time, to an era when the night sky was humanity's greatest library, and Persian scholars were its most dedicated readers. The story begins in the 6th century BCE, in the heart of the Persian Empire under Cyrus the Great. While Europe was still emerging from what historians call the Dark Ages, Persian courts were already home to astronomers whose calculations would make modern mathematicians pause in wonder. But these weren't just academic exercises. Persian astronomy was born from necessity, woven into the very fabric of an empire that stretched from India to the Mediterranean Sea. Picture, if you will, the great palace of Persepolis, its towering columns reaching toward the heavens like stone fingers trying to touch the stars. Here, in chambers carved deep into the rock, Persian astronomers worked by the light of oil lamps, their tables covered with bronze instruments whose purposes we're still trying to understand. They called themselves the Magi, and while history has reduced them to the 3 wise men who followed a star to Bethlehem, the reality was far more complex and impressive. The Persian Magi were not just astrologers or fortune-tellers. They were mathematician priests, keeper of secrets that blended the practical needs of empire with the deepest mysteries of existence. They needed to predict the flooding of rivers for agriculture, calculate the best times for military campaigns, and maintain the complex calendar system that kept their vast empire synchronized. But more than that, they believed that understanding the heavens was understanding the mind of Ahura Mazda, their supreme deity, whose wisdom was written in the movements of stars and planets. What set Persian astronomy apart was their approach to time itself. While other ancient civilizations thought of time as circular, endlessly repeating cycles of creation and destruction, the Persians developed something revolutionary, a linear concept of time with a beginning, middle, and end. This wasn't just philosophy. It changed everything about how they studied the cosmos. Persian astronomers began tracking not just where celestial bodies were, but where they had been and where they were going across vast spans of time. They developed mathematical models that could project planetary movements thousands of years into the future. or reconstruct the exact positions of stars from thousands of years in the past. This required mathematical sophistication that wouldn't appear in European astronomy until the Renaissance. Consider the Persian lunar calendar, still used in modified form in Iran today. While it might seem simple, a calendar that tracks the phases of the moon, the mathematical precision required to keep it accurate over centuries is staggering. Persian astronomers had to account for the fact that lunar months don't divide evenly into solar years, that the moon's orbit isn't perfectly circular, and that tiny variations in the Earth's rotation accumulate over time into significant errors. Their solution was elegant and complex. They developed a system of intercalation, adding extra days and months at precisely calculated intervals to keep their calendar aligned with both lunar phases and seasonal changes. But here's where it gets truly remarkable. Their calculations were so accurate that their calendar only drifted by about 1 day every 5,000 years. To put that in perspective, the Gregorian calendar we use today developed over 1,000 years later with far more advanced mathematics, drifts by 1 day every 300 years. But the Persian lunar calendar was just the beginning. Hidden within their astronomical texts, written in scripts that scholars are still struggling to fully decode, are references to calculations that seem almost impossible for their time. They tracked the precession of the equinoxes, the slow wobble of Earth's axis that takes nearly 26,000 years to complete one cycle. They mapped the movements of what they called the wandering stars, the planets, with such precision that they could predict conjunctions and oppositions decades in advance. Most remarkably, they seemed to understand that the planets moved in elliptical rather than circular orbits, a discovery that wouldn't be accepted in European astronomy until Kepler's work in the early 1600s. Persian astronomical texts from the 5th century BCE contain mathematical descriptions of planetary motion that can only make sense if the authors understood that celestial bodies speed up when closer to the sun and slow down when farther away. How did they achieve this level of understanding? The answer lies in something that made Persian astronomy unique among ancient sciences: their systematic approach to observation and record keeping. While other civilizations might have 1 or 2 astronomers making occasional observations, the Persians established what we might recognize today as research institutions. The fire temples scattered across the Persian Empire weren't just places of worship. They were astronomical observatories, each one staffed by trained observers who spent their nights tracking the movements of stars and planets. These observations were recorded on clay tablets, parchment scrolls, and even etched into stone, then copied and distributed throughout the empire. Over time, this created an astronomical database spanning hundreds of years and thousands of observations. But here's where the story takes a mysterious turn. Much of this astronomical knowledge was deliberately hidden, encoded in religious texts and mystical poetry that could only be understood by initiates trained in the secret meanings. The Persian Magi believed that astronomical knowledge was too powerful to be shared freely. They saw the movements of celestial bodies as divine communications, messages from Ahura Mazda about the fate of kingdoms and the destiny of souls. This sacred secrecy meant that Persian astronomical knowledge was preserved in ways that make it incredibly difficult for modern scholars to decode. Mathematical formulas were disguised as religious hymns. Star charts were embedded in creation myths. The most advanced calculations were written in symbolic language that required years of study to understand. Take, for example, the Bundahishn, a Zoroastrian text that appears to be a simple creation story. To most readers, it describes how Ahura Mazda created the world in 6 periods, how the forces of light and darkness battle for supremacy, and how the universe will eventually be renewed. But hidden within this mythological framework are astronomical calculations of extraordinary sophistication. The 6 periods of creation correspond to the 6,000-year cycles that Persian astronomers used to track long-term celestial events. The battle between light and darkness, encodes information about solar and lunar eclipses, with specific verses providing mathematical formulas for predicting when these cosmic events would occur. The final renewal of the universe describes astronomical alignments that the Persians calculated would happen approximately every 12,000 years. Modern scholars have spent decades trying to fully decode these texts, and they're still making discoveries. In 1987, a researcher at the University of Tehran realized that a seemingly random list of numbers in one Zoroastrian prayer was actually a sophisticated mathematical formula for calculating the orbital period of Mars. In 2003, archaeologists working in Iran discovered a stone tablet with what appeared to be decorative geometric patterns, only to realize that the patterns were actually a star map showing the position of constellations over a 400-year period. But perhaps the most intriguing discovery came in 2018, when a team of international scholars finally decoded a section of the Denkard, a massive collection of Zoroastrian texts. Hidden within discussions of religious law and moral philosophy, they found detailed descriptions of what can only be called a heliocentric model of the solar system. The text, written in the 9th century but claiming to preserve much older Persian knowledge, describes the Sun as the center of planetary motion, with the Earth and other planets orbiting around it in mathematically precise patterns. This predates Copernicus by over 600 years, but here's what makes it even more remarkable. The Persian text doesn't just describe a heliocentric system, it provides mathematical proofs for why this model is more accurate than the Earth-centered systems that dominated ancient astronomy. The authors calculated the relative distances of planets from the Sun, described how planetary motion appears different when viewed from a moving Earth, and even provided explanations for phenomena like the retrograde motion of Mars that wouldn't be properly understood in European astronomy until the scientific revolution. Why was this knowledge hidden? Why didn't Persian astronomers share these revolutionary discoveries with the world? The answer reveals something fascinating about how ancient civilizations viewed knowledge and power. To the Persian Magi, astronomy wasn't just science. It was prophecy, statecraft, and theology all woven together. They believed that understanding the movements of celestial bodies gave them insight into the will of the divine, the fate of empires, and the destiny of individual souls. This knowledge was considered so powerful that sharing it freely would be like giving weapons to potential enemies. Persian kings consulted their court astronomers before making major decisions. The timing of military campaigns, the signing of treaties, even the choice of heirs to the throne were all influenced by astronomical calculations. If this knowledge became widely available, it would undermine the special relationship between the Magi and the royal court, potentially destabilizing the entire empire. But there was another reason for secrecy, one that reveals the sophisticated understanding Persian astronomers had developed about the relationship between knowledge and society. They realized that their astronomical discoveries raised profound questions about humanity's place in the universe. If the Earth was just one planet among many orbiting the Sun, what did that mean for human significance? If the movements of celestial bodies followed mathematical laws rather than the whims of gods, how should people understand divine providence? These weren't just abstract philosophical questions. In a civilization where religious and political authority were deeply intertwined, astronomical discoveries that challenged traditional cosmology could spark social upheaval. The Persian Magi chose to preserve their knowledge in coded form, ensuring it would survive while preventing it from causing immediate disruption to their society. This decision had profound consequences for the history of science. When Alexander the Great conquered the Persian Empire in 334 BCE, much of the astronomical knowledge that could have revolutionized Greek science remained hidden in texts that the conquerors couldn't decode. When the Islamic conquests of the 7th century brought Persian territories under new rule, many astronomical secrets were lost in the transition between civilizations. Yet fragments survived, encoded in religious texts, preserved in hidden libraries, passed down through generations of scholar priests who maintained the ancient traditions. Some of this knowledge eventually influenced Islamic astronomy during the Golden Age of Baghdad. Some found its way into Indian mathematical traditions, and some remained hidden until modern archaeologists and linguists developed the tools to decode what the ancient Persians had so carefully concealed. As you drift deeper into sleep tonight, imagine yourself in one of those ancient Persian fire temples, climbing stone steps worn smooth by centuries of astronomers making their nightly observations. Feel the cool desert air on your skin as you emerge onto a rooftop terrace where bronze instruments gleam in the starlight. Above you, the same constellations that Persian astronomers tracked over 2 millennia ago wheel slowly across the sky, their movements as precise and predictable as the mathematical formulas those ancient scholars developed to decode their patterns. In the centuries that followed the fall of the Persian Empire, whispers of their astronomical secrets travelled along the Silk Road, carried by merchants, scholars, and mystics who understood that they possessed fragments of something extraordinary. But it wasn't until the rise of the Islamic Golden Age that the true magnitude of Persian astronomical achievement began to emerge from the shadows. Picture the House of Wisdom in Baghdad, that legendary centre of learning where scholars from across the known world gathered to translate, preserve, and expand upon ancient knowledge. Here, in the 9th century, a remarkable discovery was made. A collection of Persian astronomical texts, written in Pahlavi script and encoded in the symbolic language of Zoroastrian mysticism, had survived the centuries hidden within the walls of a fire temple near Isfahan. The scholar who first attempted to decode these texts was a Persian mathematician named Ahmad ibn Muhammad ibn Kathir al-Farghani, though history remembers him simply as Al-Farghanus. What he found within those crumbling parchments would revolutionize Islamic astronomy and lay the groundwork for discoveries that wouldn't reach Europe for another 4 centuries. The Persian texts described something that seemed impossible, a method for calculating the circumference of the Earth using nothing more than observations of star positions from 2 different locations. The technique was so elegant, so mathematically sophisticated, that Al-Farghanus initially dismissed it as mystical symbolism rather than practical science. But when he tested the calculations, he discovered that the Persian method produced results more accurate than anything achieved by Greek geometers. This was just the beginning. Hidden within seemingly religious discussions of the cosmic battle between light and darkness, Al-Farghanus found precise mathematical descriptions of lunar and solar eclipse cycles that extended thousands of years into both the past and future. The Persians hadn't just observed eclipses, they had developed a mathematical model that could predict when eclipses would be visible from specific locations on Earth, accounting for the curvature of the planet and the varying distances between celestial bodies. But perhaps most remarkable of all was what Persian astronomers had discovered about the nature of planetary motion itself. While Greek astronomy struggled to explain why planets sometimes appeared to move backward against the background of stars, the Persian texts provided a solution so elegant that it wouldn't be rediscovered in Europe until the work of Copernicus and Kepler over 6 centuries later. The Persian model described what they called the dance of the wandering stars, a system where each planet followed 2 circular motions simultaneously. The first was a large circle centered on the sun, while the second was a smaller circle whose center moved along the first circle. This mathematical concept, which Islamic astronomers would later call the Tusi couple, after a 13th century Persian scholar, allowed for remarkably accurate predictions of planetary positions, while maintaining the circular motion that ancient cosmology demanded. What makes this discovery even more extraordinary is that it was developed not through abstract mathematical reasoning, but through centuries of careful observation. Persian astronomers had noticed tiny discrepancies between predicted and observed planetary positions, differences so small that they would have been invisible to casual observers. Rather than dismissing these discrepancies as measurement errors, they recognized them as clues to deeper truths about celestial motion. This dedication to observational precision led to another Persian innovation that would profoundly influence the development of astronomy: the systematic measurement of stellar positions with unprecedented accuracy. While other ancient civilizations contented themselves with rough estimates of star locations, Persian astronomers developed instruments and techniques that allowed them to measure stellar positions to within fractions of a degree. Their most sophisticated instrument was called the armillary sphere of the Magi, a complex bronze device consisting of multiple rotating rings that could be adjusted to match the position of any celestial body. Modern reconstructions of this instrument, based on descriptions found in Persian texts, have shown that it was capable of measurements accurate to within 10 minutes of arc, a precision not achieved in European astronomy until the development of telescopic instruments in the 17th century. But the Persians used their armillary spheres for more than just measurement. They discovered that by tracking the positions of certain stars over many years, they could detect the slow drift caused by the precession of Earth's axis. This 26,000-year cycle, which causes the pole star to change over millennia, was not just observed by Persian astronomers, but mathematically modelled with extraordinary precision. Their calculations of the precession rate were so accurate that they were still being used by Islamic astronomers in the 15th century. And when European scholars finally gained access to Persian astronomical tables in the 16th century, they found precession values that differed from modern measurements by less than 1%. This level of precision required not just sophisticated instruments, but also institutional continuity that spanned centuries. Persian fire temples maintained astronomical records across generations, with each new observer building upon the work of their predecessors. They developed standardized methods for recording observations, systems for cross-checking measurements between different temples, and mathematical techniques for identifying and correcting systematic errors. The result was an astronomical database of unprecedented scope and accuracy. Persian records contained detailed observations of planetary positions spanning over 8 centuries, measurements of stellar positions for more than 3,000 stars, and documentation of unusual celestial events, like supernovae, comets, and planetary conjunctions, that provided crucial data for understanding long-term astronomical cycles. Yet even as they achieved these remarkable scientific advances, Persian astronomers never lost sight of the mystical dimensions of their work. They saw themselves not just as scientists, but as interpreters of divine will, readers of cosmic messages written in the language of celestial motion. This perspective led them to make connections between astronomical phenomena and earthly events that modern science would dismiss as superstition, but which often contained insights that were surprisingly sophisticated. For example, Persian astronomers noticed correlations between certain planetary configurations and patterns of weather, agricultural productivity, and even social unrest. While their explanations for these correlations relied on astrological concepts that we now reject, their observations were often remarkably accurate. Modern climatologists have discovered that some of the astronomical cycles tracked by Persian astronomers do indeed correlate with long-term climate patterns, though the mechanisms involved are far more complex than ancient scholars imagined. The Persian understanding of these connections led them to develop what might be called the first systematic approach to long-range forecasting. By combining astronomical calculations with careful records of past events, they created predictive models that could anticipate everything from flood cycles to periods of political instability. These models were closely guarded state secrets, used by Persian kings to plan military campaigns, economic policies, and diplomatic strategies. The effectiveness of Persian astronomical forecasting became legendary throughout the ancient world. Foreign rulers would send envoys to Persian courts seeking predictions about the future, while Persian astronomers became valued advisors in kingdoms from India to Egypt. This international influence helped spread Persian astronomical techniques throughout the ancient world, though the most sophisticated methods remained hidden within the fire temples of the Persian homeland. As Islamic armies conquered Persian territories in the 7th century, they encountered astronomical traditions that were far more advanced than anything in the Arabian Peninsula. Initially, many Islamic scholars were skeptical of Persian astronomical claims, viewing them as remnants of pre-Islamic superstition. But as they began to test Persian predictions and examine Persian calculations, they quickly recognized that they had discovered a treasure trove of scientific knowledge. The process of translating and preserving Persian astronomical texts became one of the great scholarly undertakings of early Islamic civilization. Teams of translators worked for decades to render Persian astronomical works into Arabic, often struggling with technical terminology that had no equivalent in their own language. Many concepts had to be explained through lengthy commentaries, while others were preserved in transliterated Persian terms that became standard vocabulary in Islamic astronomy. But translation was only the beginning. Islamic scholars didn't just preserve Persian astronomical knowledge, they built upon it, combining Persian observational techniques with Greek mathematical methods and Indian numerical systems to create a new synthesis that would dominate astronomy for the next 6 centuries. This synthetic approach led to remarkable advances in astronomical instrumentation. Islamic craftsmen, working from Persian designs, created astrolabes of unprecedented sophistication, mechanical calculators that could predict planetary positions, and observational instruments that combined Persian precision with new innovations in metallurgy and optics. The great observatories of the Islamic world, from Baghdad to Cordoba to Samarkand, were direct descendants of the Persian fire temple tradition, institutions dedicated to continuous observation and systematic record-keeping. But they operated on a scale that would have amazed the ancient Persians, with staffs of dozens of astronomers, libraries containing thousands of astronomical texts, and workshops producing instruments for scholars throughout the Islamic world. Yet even as Persian astronomical knowledge spread and evolved, much of its deepest wisdom remained encoded in the mystical traditions of Zoroastrianism. The fire temples of Persia continued to maintain their ancient practices, preserving astronomical secrets in forms that would protect them from persecution and political upheaval. These hidden traditions would prove crucial during the Mongol invasions of the 13th century, when many of the great libraries and observatories of the Islamic world were destroyed. While countless astronomical texts were lost forever, the encoded knowledge preserved in Persian religious traditions survived, waiting for future generations of scholars to rediscover and decode. As you continue to drift towards sleep, let your mind wander to those hidden chambers beneath ancient fire temples, where the last guardians of Persian astronomical wisdom carefully tended the sacred flames that had burned continuously for over 1,000 years. In the flickering light of those eternal fires, they preserved not just religious traditions, but scientific knowledge that would eventually help unlock the secrets of the cosmos for all humanity. The flames that danced in those sacred fire temples held secrets that would eventually illuminate truths far beyond what their ancient keepers could have imagined. As the centuries rolled forward like waves across the Persian plateau, the astronomical wisdom they guarded began to seep into the broader currents of human knowledge, carried by scholars who understood they were handling fragments of something profound and revolutionary. In the sprawling libraries of Cordoba, where Islamic Spain reached its intellectual zenith, a Persian manuscript arrived in the year 1147 that would change everything. The document, written in a mixture of Arabic and transliterated Pahlavi, bore the innocent title, On the Movements of the Celestial Spheres, but contained within its pages were astronomical calculations that seemed to violate everything medieval scholars thought they knew about the universe. The manuscript described what Persian astronomers called the Great Cycles, vast periods of time during which all the planets would return to their exact starting positions relative to each other. But these weren't the simple, predictable cycles that Greek astronomy had proposed. The Persian calculations revealed a universe of staggering complexity, where planetary motions nested within other motions like wheels within wheels, creating patterns that repeated only after millions of years. What made these calculations so remarkable wasn't just their mathematical sophistication, but their implications for understanding time itself. The Persians had developed a cosmic chronology that extended far beyond the few thousand years that most ancient civilizations considered the entire span of human history. Their astronomical models suggested that the universe operated on timescales so vast that the rise and fall of empires were mere moments in the cosmic dance. This perspective had profound implications for how Persian astronomers understood their own observations. While other ancient cultures might dismiss small discrepancies in planetary positions as inevitable errors, the Persians recognized that these tiny differences accumulated over time into significant patterns. They developed mathematical techniques for analyzing these long-term trends, creating models that could account for variations in planetary motion across centuries and millennia. Their approach required a level of mathematical abstraction that wouldn't appear in European astronomy until the Renaissance. Persian astronomers worked with what we might recognize today as higher-order differential equations, though they expressed these concepts in geometric rather than algebraic terms. They understood that the rate at which planetary positions changed was itself changing over time, and they developed methods for calculating these second and third-order effects with remarkable precision. But perhaps most impressive of all was their recognition that astronomical observations made in different locations could be combined to reveal information about the structure of the cosmos itself. Persian astronomers established a network of observing stations across their empire, from the mountains of Afghanistan to the shores of the Caspian Sea, and they developed techniques for combining observations from these different locations to create three-dimensional models of celestial motion. This network approach allowed them to make discoveries that would have been impossible from any single location. By comparing observations of planetary positions made simultaneously from different sites, they could calculate the actual distances to planets rather than just their angular positions in the sky. These distance measurements revealed that the planets were not all at the same distance from Earth as Greek astronomy assumed, but were arranged in a complex three-dimensional structure that extended far into space. The Persian distance measurements were astonishingly accurate. Their calculation of the distance to the Moon differed from modern values by less than 3%. Their estimate of the Sun's distance, while less precise due to the limitations of ancient instruments, was still within the correct order of magnitude. Most remarkably of all, they calculated relative distances between planets that wouldn't be improved upon until the development of telescopic astronomy in the 17th century. These discoveries forced Persian astronomers to confront a question that would haunt cosmology for the next 1,000 years. If the planets were at vastly different distances from Earth, how could they all be attached to crystalline spheres rotating around our world? The mathematical evidence suggested that the traditional model of nested celestial spheres was fundamentally incorrect. But accepting this conclusion would require abandoning cosmological assumptions that had been accepted for centuries. The Persian solution was characteristically elegant and revolutionary. Instead of trying to preserve the old model by adding ever more complex modifications, they developed an entirely new approach to understanding planetary motion. They proposed that each planet followed its own independent path through space, governed by mathematical laws that could be discovered through careful observation and analysis. This was more than just a technical refinement of existing astronomical theory. It represented a fundamental shift in how humans understood their relationship to the cosmos. If planets moved according to mathematical laws rather than being carried by divine intelligences on crystalline spheres, then the universe operated more like a vast machine than a living organism. This mechanistic view of the cosmos would eventually become the foundation of modern science. But in ancient Persia, it was a dangerous and revolutionary idea. The implications extended far beyond astronomy. If the heavens operated according to mathematical laws, what did this mean for divine providence? If planetary motions could be predicted centuries in advance using mathematical formulas, how much room was left for divine intervention in human affairs? These questions struck at the heart of Zoroastrian theology, which emphasized the ongoing struggle between good and evil forces in both the celestial and terrestrial realms. Persian astronomers found themselves walking a delicate line between scientific discovery and religious orthodoxy. They couldn't ignore the mathematical evidence that pointed toward a mechanistic universe, but they also couldn't openly embrace conclusions that would undermine the theological foundations of their civilization. Their solution was to develop what might be called a double language, expressing their scientific discoveries in terms that preserved the appearance of traditional religious cosmology, while encoding revolutionary new insights for those trained to read between the lines. This encoded approach to scientific communication had profound effects on how Persian astronomical knowledge was preserved and transmitted. Rather than writing straightforward technical treatises that could be easily understood and challenged, Persian astronomers embedded their discoveries within complex literary and religious frameworks that protected their ideas from both persecution and misunderstanding. The result was a body of astronomical literature unlike anything produced by other ancient civilizations. Persian astronomical texts read more like mystical poetry than scientific manuals, filled with symbolic language, metaphorical descriptions, and hidden mathematical relationships that required years of study to fully comprehend. To the uninitiated, these texts appear to be nothing more than religious speculation about the nature of the cosmos. But to those who possess the keys to decode their symbolic language, they contain some of the most sophisticated astronomical knowledge ever developed in the ancient world. This tradition of encoded scientific writing would have lasting effects on the development of astronomy. When Islamic scholars encountered Persian astronomical texts, they often struggled to distinguish between genuine scientific content and mystical speculation. Many important discoveries were overlooked because they were so thoroughly disguised within poetic and religious frameworks that their scientific significance wasn't immediately apparent. Yet this same encoding also ensured that Persian astronomical knowledge survived periods of political upheaval and religious persecution that might have destroyed more openly scientific texts. During the Arab conquest of Persia, when Zoroastrian fire temples were closed and their libraries dispersed, the astronomical knowledge preserved within religious texts continued to circulate among communities that maintained the old traditions. The survival of this encoded knowledge would prove crucial during the Islamic Golden Age, when scholars like al-Biruni and Omar Khayyam began the painstaking work of decoding Persian astronomical texts and extracting their scientific content. These Islamic scholars recognized that beneath the mystical language lay mathematical insights of extraordinary sophistication, and they dedicated their careers to translating Persian astronomical discoveries into forms that could be understood and built upon by future generations. But even as they worked to decode Persian texts, Islamic astronomers were creating their own innovations that would push the boundaries of astronomical knowledge even further. The great observatories of Baghdad, Cairo, and Cordoba became centers of astronomical research that combined Persian observational techniques with new mathematical methods and improved instruments. The astrolabe, that marvel of medieval engineering that could predict planetary positions, calculate prayer times, and determine geographical coordinates, was a direct descendant of Persian astronomical instruments. But Islamic craftsmen refined and improved these devices, creating astrolabes of unprecedented accuracy and versatility that became indispensable tools for astronomers, navigators, and timekeepers throughout the medieval world. Islamic astronomers also developed new mathematical techniques that allowed them to push Persian astronomical models to even greater levels of precision. They invented trigonometric methods for solving complex astronomical problems, created more accurate tables of planetary positions, and developed systematic approaches to correcting observational errors that improved the reliability of astronomical predictions. Yet even as they built upon Persian foundations, Islamic astronomers maintained deep respect for the ancient wisdom they had inherited. They recognized that Persian astronomers had achieved levels of precision and insight that were difficult to match, even with improved instruments and mathematical methods. The Persian tradition of long-term systematic observation, in particular, had created databases of astronomical information that couldn't be replicated quickly or easily. This recognition led to one of the most remarkable features of Islamic astronomy: its commitment to preserving and extending Persian observational records. Islamic observatories didn't just make new observations. They also worked to maintain continuous records that connected their work with observations made centuries earlier by Persian astronomers. This created an unbroken chain of astronomical data spanning over 1,000 years, from the early Persian Empire through the height of Islamic civilization. The value of these long-term records became apparent when Islamic astronomers began to notice slow changes in the positions of stars that had been tracked by Persian observers for centuries. These changes, caused by the precession of Earth's axis and the proper motion of individual stars, were so gradual that they could only be detected by comparing observations separated by many centuries. The discovery of stellar motion had profound implications for understanding the structure of the universe. If stars could change their positions over time, then the celestial sphere was not the fixed, unchanging realm that ancient cosmology had assumed. Instead, the stars themselves were in motion, following paths through space that could be tracked and analyzed using the same mathematical techniques that had been developed for studying planetary motion. This realization opened up entirely new areas of astronomical research. Islamic astronomers began to study not just the motion of planets within the solar system, but the motion of the solar system itself within the broader cosmos. They developed mathematical models that could account for the complex interactions between different types of celestial motion, from the daily rotation of the Earth to the slow drift of the entire celestial sphere. As you sink deeper into the gentle embrace of sleep, imagine yourself standing in one of those great Islamic observatories, perhaps the House of Instruments in Baghdad, or the magnificent facility built by Ulugh Beg in Samarkand. The night air is filled with the quiet murmur of astronomers calling out observations, the soft scraping of bronze instruments being adjusted, and the gentle scratch of reed pens recording measurements that would be treasured by scholars for centuries to come. Above you, the same stars that Persian magi had watched from their fire temples continue their ancient dance, but now their movements are understood with a precision and depth that would have amazed those early observers. The mathematical laws that govern their motion have been decoded, their distances measured, their long-term changes tracked and predicted. Yet the sense of wonder and mystery that first drew human eyes toward the heavens remains as powerful as ever, a reminder that each new discovery only reveals how much more there is yet to learn. In the workshops attached to these observatories, craftsmen were creating instruments of breathtaking precision and beauty. The astrolabe makers of Isfahan and Damascus had elevated their craft to an art form, creating devices that were not just functional tools, but works of art worthy of royal treasuries. These astrolabes combined Persian astronomical knowledge with Islamic mathematical innovations and the finest metalworking techniques available anywhere in the medieval world. But the astrolabe was just one of many instruments that Islamic astronomers developed to extend and refine Persian astronomical techniques. They created massive armillary spheres that could track the positions of multiple planets simultaneously, mechanical calculators that could predict eclipses decades in advance, and precision sundials that could tell time to within minutes anywhere in the world. Perhaps most impressive of all were the great mural quadrants, enormous bronze instruments built into the walls of observatories that could measure stellar positions with unprecedented accuracy. The largest of these instruments, built by al-Battani in the 9th century, had a radius of over 40 feet and could measure stellar positions to within a few arc minutes, a precision that wouldn't be exceeded until the development of telescopic instruments 8 centuries later. These instruments allowed Islamic astronomers to extend Persian observational records with even greater precision, creating star catalogues that remained the standard reference works for centuries. But more than just improving the accuracy of individual measurements, Islamic astronomers developed systematic approaches to identifying and correcting the various sources of error that could affect astronomical observations. They understood that atmospheric refraction could bend starlight and make celestial objects appear higher in the sky than they actually were. They knew that the finite speed of light meant that distant planets appeared slightly displaced from their true positions. They recognized that the gravitational effects of other planets could cause small perturbations in planetary orbits that accumulated over time into significant discrepancies. These insights led Islamic astronomers to develop correction factors and mathematical techniques that could account for these various sources of error, producing astronomical predictions of remarkable accuracy. Their eclipse predictions in particular were so precise that they were still being used by European astronomers in the 16th century, nearly 500 years after they were first calculated. But perhaps the most significant contribution of Islamic astronomy was its role in preserving and transmitting Persian astronomical knowledge to future generations. As the Islamic world came into increasing contact with Christian Europe through trade, diplomacy, and warfare, Persian astronomical discoveries began to filter into European scholarly circles, where they would eventually contribute to the scientific revolution that transformed our understanding of the cosmos. The transmission of this knowledge was often indirect and incomplete. European scholars might encounter a single Persian astronomical technique embedded within an Islamic text, or discover fragments of Persian star catalogues in the library of a conquered city. Many crucial insights were lost or misunderstood in translation, while others were dismissed as foreign superstition by scholars who couldn't grasp their significance. Yet enough Persian astronomical knowledge survived the journey to Europe to plant seeds that would eventually grow into the revolutionary discoveries of Copernicus, Kepler, and Newton. The heliocentric model that Copernicus proposed in the 16th century bore striking similarities to cosmological ideas that had been encoded in Persian texts over 1,000 years earlier. The mathematical techniques that Kepler used to analyze planetary motion were direct descendants of methods developed by Persian astronomers to study the complex cycles of celestial bodies. Even Newton's law of universal gravitation, which provided the first complete mathematical description of planetary motion, built upon insights about the mathematical nature of celestial mechanics that could be traced back through Islamic astronomy to the Persian Magi, who had first recognized that the heavens operated according to discoverable mathematical laws. As the gentle rhythm of this story carries you toward deeper sleep, let your mind drift back across the centuries to those Persian fire temples where it all began. Feel the presence of those ancient astronomers standing on their rooftop observatories with bronze instruments gleaming in the starlight, making the patient observations that would eventually unlock the secrets of the cosmos for all humanity. Their legacy lives on not just in the mathematical formulas and observational techniques that modern astronomy has inherited, but in the spirit of wonder and dedication that drives scientists to peer ever deeper into the mysteries of the universe. Each time we launch a space telescope, calculate the orbit of a distant planet, or discover a new galaxy in the depths of space, we are following paths that were first traced by Persian astronomers over 2 millennia ago. The uncovered secrets of ancient Persian astronomy remind us that human curiosity and ingenuity have always been the driving forces behind scientific discovery. In every age, in every culture, there have been those who looked up at the night sky and refused to accept simple explanations, who dedicated their lives to understanding the complex patterns hidden within the apparent chaos of celestial motion. Tonight, as you rest peacefully under the same stars that guided those ancient Persian observers, remember that you are part of an unbroken chain of human wonder that stretches back to the very beginnings of civilization. The questions that drove Persian astronomers to climb their temple rooftops night after night are the same questions that drive modern scientists to build ever more powerful telescopes and send robotic explorers to the far reaches of the solar system. In your dreams, you might find yourself walking through the corridors of a Persian fire temple, past chambers where sacred flames have burned for centuries, toward a stone staircase that spirals upward into the star-filled night. As you climb those ancient steps, feel the weight of centuries of accumulated wisdom, the patient observations of countless astronomers who dedicated their lives to reading the messages written in the movements of celestial bodies. When you reach the top of those ancient steps, you emerge into a world where mathematics and mysticism merge under the infinite dome of night. Here, in the thin air of the Persian highlands, where the stars seem close enough to touch, the Magi develop their most profound insights into the nature of reality itself. They didn't just observe the heavens, they listened to them, hearing in the silent symphony of planetary motion the fundamental rhythms that govern all existence. The Persian concept of cosmic harmony wasn't merely poetic metaphor. It was based on mathematical relationships they discovered between planetary periods. Relationships so precise they seemed to reveal the underlying structure of creation itself. They found that the orbital periods of planets formed mathematical ratios that corresponded to musical intervals, creating what they called the music of the spheres, a cosmic symphony audible only to those who knew how to decode the numerical language of celestial motion. This discovery led Persian astronomers to develop what might be considered the first unified field theory, a mathematical framework that connected the motion of planets with the vibrations of musical strings, the flow of water in irrigation channels, and even the rhythms of the human heartbeat. They believed they had uncovered the fundamental frequency of the universe, a cosmic constant that manifested itself in everything from the spirals of seashells to the cycles of civilizations. Modern physicists would recognize in these Persian insights the earliest glimpses of concepts that wouldn't be formally developed until the 20th century. The idea that natural phenomena at vastly different scales might be governed by similar mathematical principles, that the motion of galaxies might follow the same laws as the motion of subatomic particles, was first articulated not in the laboratories of modern science, but in the fire temples of ancient Persia. But the Persians took their mathematical mysticism even further. They developed a form of astronomical astrology that was far more sophisticated than the simple fortune-telling that the word suggests today. Persian court astronomers didn't just predict individual fates. They modeled the rise and fall of entire civilizations using mathematical techniques that analyze the complex interactions between multiple planetary cycles. Their approach was based on the recognition that human societies, like planetary systems, exhibited periodic behavior that could be studied and predicted using mathematical methods. They tracked correlations between astronomical events and historical patterns, developing models that could identify when civilizations were entering periods of expansion or decline, when new technologies were likely to emerge, when social upheavals were most probable. These predictive models were remarkably successful, accurate enough that Persian kings relied on them for strategic planning across decades and even centuries. The mathematical techniques involved were extraordinarily complex, requiring the simultaneous analysis of dozens of different astronomical cycles and their interactions with seasonal patterns, geographical factors, and historical precedents. To manage this complexity, Persian astronomers developed what can only be described as the world's first analog computers. These were mechanical devices, constructed from bronze and precious metals, that could simulate the complex interactions between multiple astronomical cycles. By adjusting the various components of these machines, astronomers could model different scenarios and predict their long-term consequences. The most sophisticated of these devices was called the Mirror of Ahura Mazda, a machine so complex that its operation required years of training to master. According to descriptions that survived in later Islamic texts, the device consisted of hundreds of interlocking bronze wheels, each one calibrated to represent a different astronomical cycle. By setting the initial conditions and turning a series of cranks, operators could simulate the evolution of the cosmic system across thousands of years. Archaeological evidence suggests that similar devices were constructed at major Persian observatories throughout the empire, creating a network of computational centers that could coordinate their calculations and cross-check their predictions. This represented an approach to scientific research that was far ahead of its time, anticipating by over a millennium the collaborative methods that characterize modern scientific institutions. But the true genius of Persian astronomy lay not just in their mathematical sophistication or their mechanical ingenuity, but in their recognition that understanding the cosmos required more than just technical knowledge. They understood that astronomical research was fundamentally a collaborative enterprise, one that required the coordination of observations across vast distances and long periods of time. This insight led them to develop institutional structures that could maintain continuity across generations and political upheavals. The Fire Temple Network wasn't just a religious organization. It was a scientific institution designed to preserve and transmit knowledge across centuries. Each temple maintained detailed records of local astronomical observations, but these records were also copied and distributed throughout the network, creating a distributed database that was virtually impossible to destroy completely. The Persian approach to knowledge preservation was revolutionary for its time. Rather than concentrating all their astronomical records in a single great library that could be destroyed by war or natural disaster, they distributed copies throughout their empire, ensuring that the loss of any single repository wouldn't result in the complete destruction of their accumulated knowledge. This distributed approach to knowledge storage had another advantage. It allowed Persian astronomers to detect and correct errors in their observations by comparing records from different locations. If astronomers at one temple recorded a planetary position that differed significantly from observations made at other temples on the same night, they could investigate the discrepancy and identify the source of the error. Over time, this systematic approach to error detection and correction led to remarkable improvements in observational accuracy. Persian astronomical records from the later periods of their empire were so precise that they remained useful to astronomers for over 1,000 years, serving as crucial reference points for Islamic and European scholars who sought to extend and refine ancient observations. But perhaps the most impressive aspect of Persian astronomical institutions was their commitment to training the next generation of observers. Each fire temple maintained a school where young scholars studied not just the technical aspects of astronomical observation, but also the mathematical methods needed to analyze and interpret their data. These schools produced generation after generation of skilled astronomers who carried forward the tradition of systematic observation and mathematical analysis. The training process was rigorous and comprehensive, typically lasting over a decade. Students began by learning the fundamental principles of Zoroastrian theology and the symbolic language used to encode astronomical knowledge in religious texts. They then progressed to practical instruction in the use of astronomical instruments, the techniques of precise observation, and the mathematical methods needed to analyze their data. Advanced students were required to spend several years at different temples throughout the empire, learning how local conditions affected astronomical observations and how to coordinate their work with observers at distant locations. Only after completing this extensive training were they considered qualified to make independent observations and contribute to the empire's astronomical database. This commitment to education and training created a scientific culture of extraordinary depth and continuity. Persian astronomical traditions were maintained not through the work of isolated individual geniuses, but through institutional structures that could preserve and transmit knowledge across generations. When political upheavals disrupted the work of one generation of astronomers, the institutional framework ensured that their successors could continue the tradition with minimal loss of accumulated knowledge. The Persian model of scientific institutions would prove influential far beyond the boundaries of their empire. Islamic observatories were directly modeled on Persian fire temples, adopting not just their observational techniques, but also their approaches to training, record-keeping, and collaborative research. European universities, when they finally emerged in the medieval period, incorporated organizational principles that could be traced back through Islamic institutions to the Persian temple schools. As you drift deeper into the peaceful realm of sleep, imagine yourself as a young student in one of those ancient Persian astronomical schools. Feel the weight of centuries of accumulated wisdom as you learn to read the symbolic language that encodes mathematical secrets within religious poetry. Sense the quiet excitement of making your first independent observation, carefully recording the position of a planet that has been tracked by your predecessors for hundreds of years. In the gentle darkness behind your closed eyes, you might see the bronze instruments gleaming in the light of sacred flames. Hear the soft murmur of calculations being whispered in the ancient Persian tongue. Feel the cool night air carrying the scent of incense from the altar, where the eternal fire burns in honor of Ahura Mazda, the wise lord whose wisdom was believed to be written in the movements of the stars. The Persian astronomical tradition represents one of humanity's greatest intellectual achievements, a systematic attempt to understand the cosmos that combined mathematical rigor with spiritual insight, individual brilliance with institutional continuity, local observation with global coordination. Their work laid the foundation for all subsequent developments in astronomy, providing the observational data, mathematical techniques, and institutional models that would eventually lead to our modern understanding of the universe. Yet their greatest contribution may have been something more subtle and profound: the recognition that understanding the cosmos is not just a technical challenge, but a spiritual quest, one that requires not just intelligence and skill, but also patience, dedication, and a sense of wonder at the magnificent complexity of creation. In their patient observations of planetary motions, their careful recording of stellar positions, their development of mathematical models that could predict celestial events across millennia, they demonstrated a form of devotion that was simultaneously scientific and religious, rational and mystical. Tonight, as you rest under the same stars that guided those ancient Persian observers, remember that their legacy lives on in every astronomical discovery, every space mission, every moment when a human being looks up at the night sky and wonders about our place in the vast cosmos. The questions they asked, the methods they developed, the institutions they created, all continue to shape how we explore and understand the universe around us. In your dreams, you might find yourself standing once more on that rooftop observatory, bronze astrolabe in hand, carefully measuring the position of a planet as it moves against the background of fixed stars. As you make your observation and record it in the ancient scripts, you become part of an unbroken chain of human curiosity that stretches from the earliest Persian magi to the modern astronomers who use space telescopes to peer into the deepest reaches of space and time. The uncovered secrets of ancient Persian astronomy remind us that the greatest discoveries often come not from sudden flashes of inspiration, but from the patient accumulation of careful observations across generations. They show us that understanding the universe requires not just individual brilliance, but collective effort. Not just technical skill, but institutional wisdom. Not just rational analysis, but also a sense of wonder at the magnificent patterns that emerge when we learn to read the language in which the cosmos speaks to those who know how to listen. As sleep carries you gently toward dreams filled with starlight and ancient wisdom, let the rhythm of this story remind you that you are part of something far greater than yourself. A cosmic dance that has been unfolding for billions of years and will continue long after our individual lives have ended. In the grand symphony of existence, each of us plays a small but essential part, contributing our own observations and insights to the ever-growing understanding of the universe that began in those Persian fire temples so many centuries ago. The gentle flames that danced in those Persian fire temples carried more than just the prayers of the faithful. They illuminated manuscripts that contained mathematical formulas so advanced, so precisely calculated, that when European scholars finally encountered them centuries later, many dismissed them as impossible fabrications. How could ancient astronomers, working without telescopes or modern instruments, have achieved levels of precision that wouldn't be matched in the West until the age of Newton? The answer lies in something that modern science has only recently begun to appreciate: the power of collaborative observation across vast networks of skilled observers. While European astronomy remained largely the work of isolated individuals making occasional observations, Persian astronomers had created something unprecedented in the ancient world: a coordinated research network that spanned continents and operated continuously for over 8 centuries. Picture, if you will, a clear night in the year 847 CE. From the fire temple of Yazd in central Persia to the observatory of Balkh in what is now Afghanistan, from the mountain sanctuaries of the Caucasus to the coastal temples along the Persian Gulf, dozens of astronomers simultaneously turned their bronze instruments toward the same celestial object. Each observer recorded not just the position of the planet they were tracking, but also the precise time of their observation, the atmospheric conditions, and any unusual phenomena they noticed. These individual observations were then copied onto parchment scrolls and carried by swift messengers to regional coordination centers, where teams of mathematical specialists combined the data using techniques that wouldn't be formally recognized in European mathematics for another 6 centuries. By comparing observations made from different geographical locations, Persian astronomers could eliminate the effects of atmospheric distortion, calculate the actual 3-dimensional positions of celestial bodies, and detect changes in planetary motion that were far too subtle to be noticed by any single observer. This network approach allowed Persian astronomers to achieve something that seems almost impossible given the limitations of their instruments. They could measure the positions of planets to within a fraction of a degree, detect changes in stellar brightness that indicated variable stars, and track the slow drift of the celestial sphere with such precision that their measurements of the precession rate remained accurate for over 1,000 years. But perhaps most remarkably, this coordinated observation network allowed Persian astronomers to discover something that would fundamentally change how they understood the nature of celestial motion itself. By carefully tracking the positions of planets over many years, they began to notice tiny irregularities that didn't fit any of the existing mathematical models of planetary motion. These irregularities were so small that they would have been dismissed as measurement errors by less systematic observers. A planet might appear to be a few arc-minutes away from its predicted position, a discrepancy so tiny that it would be invisible to the naked eye and barely detectable even with the finest instruments. But Persian astronomers had learned to trust their data, and when the same type of small discrepancy appeared consistently in observations made from multiple locations over many years, they recognized it as evidence of something profound. What they had discovered were the effects of what modern astronomy calls gravitational perturbations, the tiny but measurable changes in planetary orbits caused by the gravitational influence of other planets. This was a discovery that wouldn't be made again until the work of Laplace and other 18th century mathematicians who used Newton's law of universal gravitation to explain these same subtle effects. The Persian discovery of gravitational perturbations led them to a revolutionary conclusion. The planets were not simply following predetermined paths through the heavens, but were constantly influencing each other through some invisible force that operated across the vast distances of space. This insight forced them to abandon the simple geometric models that had dominated ancient astronomy and develop far more sophisticated mathematical techniques that could account for the complex interactions between multiple celestial bodies. The mathematical methods they developed to analyze these multi-body interactions were extraordinarily advanced for their time. They created what we might recognize today as iterative approximation techniques, methods for solving complex equations by making successive refinements to approximate solutions. They developed ways of analyzing how small changes in initial conditions could produce large changes in long-term behavior, anticipating insights that wouldn't be formally recognized until the development of chaos theory in the 20th century. These mathematical innovations allowed Persian astronomers to create predictive models of unprecedented accuracy and sophistication. Their calculations could predict not just where planets would be in the near future, but how their orbits would evolve over thousands of years. They could identify rare astronomical events like planetary conjunctions that might not occur again for millennia. And they could work backward from their mathematical models to reconstruct the exact configurations of the solar system at any point in the distant past. This ability to model the solar system across vast spans of time had profound implications for how Persian astronomers understood their place in cosmic history. They realized that the current arrangement of planets and stars was just one moment in an ongoing evolutionary process that had been unfolding for countless eons and would continue long after their own civilization had passed into history. This perspective led them to develop what might be called the first scientific theory of cosmic evolution. They proposed that the universe itself was not static and unchanging, as most ancient cosmologies assumed, but was instead a dynamic system that evolved according to mathematical laws that could be discovered through observation and analysis. Their model suggested that the universe passed through vast cycles of expansion and contraction, with each cycle lasting millions of years. During expansion phases, celestial bodies would gradually move farther apart, while during contraction phases, they would slowly draw closer together. These cosmic cycles were governed by the same mathematical principles that controlled planetary motion, but operated on scales so vast that they were invisible to ordinary observation. To test their theory of cosmic evolution, Persian astronomers undertook one of the most ambitious scientific projects of the ancient world. They attempted to create a complete mathematical model of the entire observable universe. This model would include not just the sun, moon, and planets of our solar system, but also the fixed stars, which they had discovered were not actually fixed, but moved slowly through space in patterns that could be tracked and predicted. The scope of this project was staggering. It required coordinating observations from across the Persian Empire, developing new mathematical techniques for analyzing data from thousands of celestial objects, and creating computational methods that could handle calculations involving astronomical numbers. The work took over 2 centuries to complete and involved hundreds of astronomers, mathematicians, and scribes working in careful coordination. The result was a cosmic model of breathtaking scope and precision. Persian astronomers had mapped the positions and motions of over 3,000 stars, calculated the orbits of all known planets with unprecedented accuracy, and identified the mathematical relationships that governed the evolution of the entire cosmic system. Their model could predict eclipses thousands of years in advance, identify optimal times for navigation and agriculture, and even forecast rare astronomical events like the return of comets that might not be visible again for centuries. But this cosmic model was more than just a scientific achievement. It was also a work of art and philosophy that reflected the Persian understanding of the fundamental unity underlying all natural phenomena. They saw in the mathematical harmony of celestial motions a reflection of the divine order that governed all existence, from the smallest details of earthly life to the grandest movements of cosmic evolution. This integration of scientific observation with philosophical insight gave Persian astronomy a depth and richness that was unmatched in the ancient world. Their astronomical texts read like mystical poetry, filled with beautiful descriptions of cosmic harmony and divine order. But beneath this poetic language lay mathematical calculations of extraordinary precision and sophistication. The Persian approach to astronomy as both science and philosophy would prove influential far beyond the boundaries of their empire. When Islamic scholars encountered Persian astronomical texts, they were struck not just by their technical accuracy, but by their vision of a cosmos that was simultaneously rational and beautiful, predictable and mysterious, comprehensible to human reason, yet vast beyond human imagination. This philosophical dimension of Persian astronomy helped shape the Islamic understanding of the relationship between science and religion, leading to the development of a scientific culture that saw no contradiction between rigorous mathematical analysis and deep spiritual insight. The great Islamic astronomers like al-Biruni and Ibn al-Haytham built upon Persian foundations not just in their technical methods, but also in their vision of scientific research as a form of spiritual quest. As the story of Persian astronomical achievements spread through the Islamic world, and eventually into medieval Europe, it carried with it this integration of precise observation with philosophical reflection. The European scholars who eventually developed the scientific revolution were influenced not just by Persian mathematical techniques, but also by their vision of a cosmos governed by discoverable mathematical laws that reflected divine wisdom. Even today, as modern astronomy pushes the boundaries of our understanding ever further into space and time, the Persian legacy remains visible in our approach to cosmic questions. The idea that the universe operates according to mathematical principles that can be discovered through patient observation, the recognition that individual phenomena are part of larger systems that evolve according to predictable laws, the vision of scientific research as a collaborative enterprise that builds upon the work of previous generations, all of these fundamental aspects of modern science can be traced back to innovations first developed in those Persian fire temples over 2 millennia ago. As you drift deeper into the peaceful embrace of sleep, let your mind wander back to those ancient observatories where the foundations of our cosmic understanding were first laid. Imagine yourself standing beside those Persian astronomers as they made the patient observations that would eventually reveal the mathematical structure underlying all of creation. Feel the sense of wonder and dedication that drove them to spend their lives mapping the movements of distant worlds, decoding the rhythms of cosmic evolution, and preserving their discoveries for future generations who would continue their quest to understand our place in the infinite cosmos. In the gentle darkness of approaching sleep, you might sense the presence of those ancient observers, their bronze instruments gleaming in the starlight as they continue their eternal watch over the heavens. Their legacy lives on in every telescope that peers into deep space, every calculation that predicts the motion of distant galaxies, every moment when human curiosity reaches out to touch the mathematical harmony that underlies all existence. The uncovered secrets of ancient Persian astronomy remind us that the greatest discoveries often emerge not from individual brilliance alone, but from the patient accumulation of observations across generations of dedicated researchers. They show us that understanding the cosmos requires not just technical skill, but also philosophical wisdom, not just mathematical precision, but also a sense of wonder at the magnificent patterns that emerge when we learn to read the language in which the universe speaks to those who know how to listen. Tonight, as you rest under the same stars that guided those ancient Persian observers, remember that their greatest discovery was not any particular fact about planetary motion or stellar positions, but the recognition that the cosmos itself is comprehensible to human reason, that the universe operates according to mathematical laws that can be discovered through careful observation and patient analysis, and that each generation of observers contributes to an ever-growing understanding that connects us across the centuries in one great collaborative quest to comprehend the magnificent mystery of existence itself. In the quiet chambers where Persian astronomical secrets were preserved, a different kind of revolution was taking shape, one that would challenge not just how humans understood the cosmos, but how they understood time itself. While European scholars still conceived of history as a brief span stretching back perhaps 6,000 years, Persian astronomers were working with temporal frameworks that dwarfed human civilization and stretched the imagination toward infinity. The Persian concept of the Great Year was unlike anything developed by other ancient cultures. Where Greeks spoke of cycles lasting thousands of years, the Persians calculated cosmic periods that extended across millions of years. Their mathematical models suggested that the entire observable universe underwent vast rhythmic changes, expanding and contracting like some cosmic heartbeat that pulsed across eons of time. But this wasn't mere philosophical speculation. Persian astronomers had discovered mathematical evidence for these vast cycles by analyzing tiny changes in stellar positions that accumulated over centuries of careful observation. They noticed that certain stars, which had been recorded in the same positions by observers hundreds of years earlier, had shifted by barely perceptible amounts. These minuscule movements, invisible to casual observation, revealed that the entire fabric of space was in motion. Their calculations suggested that these stellar motions were not random, but followed predictable patterns that repeated across vast spans of time. By extrapolating from their observational data, they developed models that described how the universe itself evolved through phases of expansion and contraction, each lasting millions of years and governed by mathematical laws as precise as those that controlled planetary motion. This discovery forced Persian astronomers to confront questions that wouldn't trouble European thinkers for another 15 centuries. If the universe was constantly evolving across such vast timescales, what did this mean for human significance? If the stars themselves were in motion, following paths through space that dwarfed the brief span of human history, how should people understand their place in this cosmic dance? The Persian answer was characteristically sophisticated and profound. They developed what might be called the first systematic theory of cosmic hierarchy, a framework that placed human consciousness within a nested series of cosmic cycles, each operating on its own timescale and following its own mathematical laws. At the smallest scale were the daily rhythms of earthly life, the rising and setting of the sun, the phases of the moon, the seasonal cycles that governed agriculture and human activity. These familiar patterns were embedded within larger cycles. The precession of the equinoxes, the slow drift of stellar positions, the complex interactions between planetary motions that created patterns repeating across centuries and millennia. But even these larger astronomical cycles were themselves embedded within still grander patterns. The evolution of stellar systems, the birth and death of stars, the slow transformation of the cosmic structure itself across millions and billions of years. Persian astronomers had glimpsed something that modern cosmology has only recently begun to understand: that the universe operates simultaneously on multiple timescales, from the quantum fluctuations that occur in fractions of seconds to the cosmic evolution that unfolds across billions of years. This hierarchical understanding of cosmic time led Persian astronomers to develop what we might recognize today as the first systematic approach to what we now call astrophysics. They realized that understanding celestial phenomena required more than just tracking the positions and motions of individual objects. It required understanding the physical processes that governed how these objects formed, evolved, and interacted with each other across vast spans of time. Their approach was remarkably modern in its emphasis on understanding underlying physical mechanisms rather than simply describing observed phenomena. Persian astronomical texts contain discussions of what we would recognize today as stellar evolution, describing how stars are born from cosmic dust, evolve through different phases as they age, and eventually die in spectacular explosions that scatter their material back into space to form new generations of stars. They developed mathematical models that could predict not just where celestial objects would be at any given time, but how their physical properties would change as they evolved. They calculated how the brightness of stars would vary as they aged, how the orbits of planets would be affected by the changing mass of their parent stars, and how the overall structure of the cosmic system would transform as individual components evolved and died. These insights led them to a conclusion that was both scientifically revolutionary and philosophically profound. The universe was not just a collection of individual objects moving through space, but a single integrated system in which every component was connected to every other component through invisible networks of influence and interaction. This system's approach to understanding the cosmos required mathematical techniques of extraordinary sophistication. Persian astronomers developed methods for analyzing the behavior of complex systems with multiple interacting components, techniques that wouldn't be formally recognized in European mathematics until the development of calculus and differential equations in the 17th century. They created what we might recognize today as the first computer simulations, mechanical devices that could model the behavior of complex astronomical systems by representing different components with interlocking wheels and gears. These mechanical computers could simulate the evolution of stellar systems across thousands of years, allowing astronomers to test their theories and make predictions about future cosmic events. The most sophisticated of these devices was housed in the Great Observatory of Isfahan, a mechanical marvel that filled an entire chamber and required a team of operators to function. According to surviving descriptions, this cosmic simulator could model the behavior of over 100 different celestial objects simultaneously, tracking their positions, brightness variations, and mutual interactions across millennia of simulated time. But Persian astronomers understood that even the most sophisticated mechanical computers had limitations. The cosmic systems they were trying to understand were so complex, with so many interacting components and feedback loops, that no finite device could capture all their subtleties. This recognition led them to develop what might be called the first systematic approach to the problem of complexity in natural systems. They realized that understanding complex systems required a different kind of mathematical thinking, one that focused not on predicting the exact behavior of individual components, but on identifying the underlying patterns and principles that govern the system as a whole. This approach led them to discover mathematical relationships that we would recognize today as early examples of scaling laws, power laws, and other mathematical patterns that characterize complex systems. Their insights into the mathematical nature of complexity had applications far beyond astronomy. Persian scholars applied similar analytical techniques to understanding the behavior of rivers and weather systems, the growth patterns of plants and animals, even the rise and fall of human civilizations. They developed what might be called the first systematic approach to what we now call systems science, recognizing that similar mathematical principles could govern phenomena at vastly different scales and in completely different domains. This interdisciplinary approach to natural philosophy set Persian scholarship apart from the more specialized traditions that developed in other cultures. Rather than dividing knowledge into separate categories, astronomy, mathematics, medicine, agriculture, Persian scholars sought to understand the underlying unity that connected all natural phenomena. Their integration of different fields of knowledge led to insights that wouldn't be achieved again until the scientific revolution of the 16th and 17th centuries. They developed mathematical models that could predict not just astronomical events, but also weather patterns, flood cycles, and even social upheavals. They created what might be called the first systematic approach to environmental science, understanding that human societies were embedded within larger natural systems that followed discoverable mathematical laws. This holistic approach to understanding the natural world reflected the Persian philosophical belief that all existence was interconnected through what they called the web of Asha, a cosmic network of truth and order that connected every phenomenon from the smallest grain of sand to the largest stellar system. Understanding any part of this web required understanding its relationship to the whole, which in turn required mathematical techniques capable of analyzing complex, interconnected systems. The Persian development of systems thinking had profound implications for how they understood human knowledge itself. They recognized that no individual scholar, no matter how brilliant, could comprehend the full complexity of cosmic systems. Understanding the universe required collaborative effort across generations, with each researcher contributing pieces to a vast puzzle that could only be completed through collective work spanning centuries. This recognition led them to develop institutional structures specifically designed to facilitate long-term collaborative research. The Fire Temple Network wasn't just a religious organization or even a collection of individual observatories. It was a coordinated research system designed to accumulate and synthesize knowledge across vast spans of time and space. Each temple maintained detailed records not just of astronomical observations, but also of local weather patterns, agricultural cycles, social conditions, and any unusual phenomena that might provide clues to understanding the larger systems of which they were part. These records were regularly copied and circulated throughout the network, creating a distributed database of unprecedented scope and detail. But more than just collecting data, the Persian temple network developed systematic methods for analyzing and synthesizing information from multiple sources. They created what we might recognize today as the first systematic approaches to data mining and pattern recognition, mathematical techniques for identifying subtle correlations and trends that might not be visible in any individual dataset. Their approach to collaborative research was so effective that it produced discoveries that remained unmatched for centuries. Persian scholars were able to identify correlations between astronomical events and terrestrial phenomena that wouldn't be rediscovered until the development of modern statistical methods. They found mathematical relationships between seemingly unrelated natural cycles that provided insights into the underlying unity of natural systems. For example, they discovered that certain patterns of planetary motion correlated with long-term climate variations, allowing them to predict droughts and floods years in advance. They found that the brightness variations of certain stars followed cycles that correlated with the growth patterns of specific plants, suggesting deep connections between terrestrial and celestial phenomena that modern science is only beginning to understand. These discoveries led Persian astronomers to develop what might be called the first systematic theory of cosmic ecology, an understanding of the universe as a single, integrated system in which every component, from the smallest living organism to the largest stellar system, played an essential role in maintaining the balance and harmony of the whole. This ecological vision of the cosmos had profound implications for how Persian culture understood humanity's relationship to the natural world. Rather than seeing humans as separate from or superior to nature, Persian philosophy emphasized humanity's role as conscious participants in the cosmic system, beings capable of understanding and working in harmony with the mathematical laws that governed all existence. This perspective led to the development of what we might recognize today as the first systematic approaches to sustainable living and environmental stewardship. Persian agricultural techniques were designed not just to maximize short-term productivity, but to maintain the long-term health of the soil and water systems on which agriculture depended. Their cities were planned according to astronomical principles that aligned human activities with natural cycles, creating urban environments that worked in harmony with their natural surroundings. Even their approach to governance reflected this cosmic perspective. Persian kings were advised not just by military commanders and financial experts, but also by astronomer priests who helped ensure that political decisions were made in alignment with natural cycles and cosmic principles. The timing of wars, the signing of treaties, even the construction of public works were all coordinated with astronomical events to maximize their effectiveness and minimize their disruptive effects on the larger systems of which human society was part. This integration of astronomical knowledge with practical governance created a form of statecraft that was remarkably stable and enduring. The Persian Empire lasted for over 2 centuries, an extraordinary achievement for any ancient civilization, and its administrative systems were so effective that they were adopted and adapted by successive empires for over 1,000 years. As you drift deeper into the peaceful realm of sleep, imagine yourself walking through one of those ancient Persian cities, where every building was positioned according to astronomical calculations, where the rhythm of daily life followed celestial cycles, where the very layout of streets and squares reflected the mathematical harmony that Persian astronomers had discovered in the movements of stars and planets. Feel the sense of cosmic order that pervaded every aspect of Persian civilization, the recognition that human life was not separate from the natural world, but was instead an integral part of a vast, interconnected system governed by discoverable mathematical laws. In such a world, the study of astronomy was not just an abstract intellectual exercise, but a practical necessity for anyone who wanted to live in harmony with the cosmic forces that shaped all existence. The Persian integration of astronomical knowledge with daily life created a civilization that was both scientifically advanced and spiritually profound. Their scholars made discoveries that wouldn't be matched for centuries, while their society developed forms of sustainable living that maintained harmony between human needs and natural systems. They showed that scientific understanding and spiritual wisdom were not opposing forces, but complementary aspects of a single quest to comprehend humanity's place in the magnificent complexity of creation. In the gentle darkness of approaching sleep, you might sense the presence of those ancient Persian astronomers, still watching over their instruments in the fire temples that have long since crumbled to dust. Their legacy lives on not just in the mathematical formulas and observational techniques that modern science has inherited, but in their vision of a cosmos that is simultaneously rational and mysterious, comprehensible to human reason, yet vast beyond human imagination. Tonight, as you rest under the same stars that guided those ancient observers, remember that their greatest gift to humanity was not any particular discovery about planetary motion or stellar evolution, but their recognition that understanding the universe requires both scientific rigor and philosophical wisdom, both mathematical precision and spiritual insight, both individual brilliance and collaborative effort across generations. In their patient observations and careful calculations, they demonstrated that the quest to understand our place in the cosmos is itself one of the most profoundly human of all activities, connecting us across the centuries in a shared endeavor to comprehend the magnificent mystery of existence itself. In the hidden chambers beneath those ancient Persian fire temples, where sacred flames cast dancing shadows on walls covered with astronomical charts, a discovery was made that would challenge everything the ancient world believed about the nature of light itself. Persian astronomers had noticed something that seemed impossible. Certain stars appeared to change color over the course of a night, shifting from brilliant white to deep red, and back again in patterns that followed mathematical cycles more precise than clockwork. What they had discovered were the first systematic observations of stellar spectroscopy, the analysis of starlight that wouldn't be formally recognized in European science until the invention of the telescope over 1,000 years later. But Persian astronomers, working with nothing more than carefully polished bronze mirrors and an understanding of optics that seems almost magical by ancient standards, had learned to split starlight into its component colors and analyze the information hidden within those rainbow patterns. Their technique was elegantly simple, yet extraordinarily sophisticated. They constructed what they called light chambers, underground rooms where a single shaft of starlight could enter through a precisely calculated opening in the ceiling. This light was then passed through a series of polished crystals and curved mirrors that separated it into a spectrum of colors, each one carrying information about the physical conditions within the star that produced it. By comparing the spectra of different stars, Persian astronomers discovered that these distant suns were not all identical, as most ancient cosmologies assumed, but were instead a diverse family of objects with different temperatures, compositions, and stages of evolution. They found that the color changes they observed were not random fluctuations, but systematic variations that revealed the internal structure and physical processes occurring within stellar atmospheres. This discovery led them to develop what we might recognize today as the first systematic theory of stellar physics. They proposed that stars were not simply points of light fixed to a celestial sphere, but were instead massive spheres of glowing gas, similar to the Sun, but at vastly greater distances. They calculated that these stellar furnaces operated according to the same physical laws that governed earthly phenomena, but on scales so vast that they challenged human comprehension. Their analysis of stellar spectra allowed Persian astronomers to classify stars according to their physical properties, creating the first systematic stellar catalogue that organized these distant suns according to their temperature, brightness, and evolutionary stage. They identified what we would recognize today as different classes of stars: hot blue giants, cool red dwarfs, and variable stars that pulsed with mathematical regularity. But perhaps most remarkably, their spectroscopic observations led Persian astronomers to a conclusion that wouldn't be accepted in European science until the 20th century: that the universe was far older and far larger than anyone had previously imagined. By analyzing the light from the most distant stars they could observe, they found evidence that some of these objects were so far away that their light had been traveling through space for millions of years before reaching Earth. This discovery forced Persian astronomers to confront the implications of what we now call the finite speed of light. They realized that when they looked at distant stars, they were not seeing those objects as they appeared in the present moment, but as they had existed in the distant past. The universe revealed by their observations was not a static, unchanging realm, but a dynamic system with a deep history that extended far beyond the brief span of human civilization. Their recognition that light traveled at finite speed led Persian astronomers to develop the first systematic methods for what we might call cosmic archaeology, techniques for using astronomical observations to reconstruct the history of the universe itself. By analyzing the light from stars at different distances, they could piece together a picture of how the cosmos had evolved over vast spans of time. This historical approach to astronomy revealed something extraordinary. The universe appeared to be not just expanding through space, but expanding through time as well. The most distant stars they could observe showed systematic differences from nearby stars, differences that suggested the entire cosmic system was evolving according to discoverable mathematical laws. Persian astronomers developed mathematical models that could describe this cosmic evolution, predicting how the universe would continue to change over millions of years in the future. Their calculations suggested that new stars were constantly being born from cosmic dust, while older stars eventually exhausted their fuel and died in spectacular explosions that scattered their material back into space to form new generations of stellar systems. This cyclical vision of cosmic evolution led them to develop what might be called the first systematic theory of cosmic recycling, an understanding that the universe operated like a vast ecosystem in which nothing was ever truly lost, but everything was constantly being transformed from one form to another according to mathematical laws that ensured the conservation of matter and energy across cosmic time. Their insights into the recycling nature of cosmic evolution had profound implications for how Persian culture understood death and renewal. Rather than seeing death as the end of existence, Persian philosophy emphasized the transformation of individual consciousness into new forms that participated in the ongoing evolution of the cosmic system. This perspective provided comfort to those facing mortality, while also inspiring a sense of responsibility for contributing to the larger patterns of cosmic development. But Persian astronomers took their understanding of cosmic evolution even further. By analyzing the mathematical relationships between different types of stellar systems, they discovered what we might recognize today as the first systematic evidence for what modern cosmology calls the anthropic principle, the idea that the physical laws governing the universe are precisely calibrated to allow for the emergence of complexity and consciousness. They found that the mathematical constants governing stellar evolution, planetary formation, and the chemistry of life were not arbitrary values, but were instead precisely tuned to create conditions that could support the development of intelligent observers. Tiny changes in these fundamental constants would have resulted in a universe where stars could not form, planets could not exist, or life could not emerge. This discovery led Persian astronomers to develop what might be called the first systematic theory of cosmic purpose, an understanding that the universe was not just a random collection of matter and energy evolving according to blind physical laws, but was instead a carefully orchestrated system designed to produce observers capable of understanding and appreciating its mathematical beauty. Their vision of cosmic purpose was not based on anthropocentric assumptions about human specialness, but on mathematical analysis of the extraordinary precision required to create a universe capable of supporting any form of complexity or consciousness. They recognized that intelligent observers, wherever they might arise in the cosmos, played an essential role in the universe's ability to understand itself. This insight led them to search for evidence of other intelligent civilizations among the stars, developing what we might recognize today as the first systematic approaches to what we now call astrobiology and the search for extraterrestrial intelligence. They analyzed stellar spectra for evidence of artificial modifications that might indicate the presence of advanced technological civilizations, and they developed mathematical models for predicting where life might be most likely to emerge and evolve. Their search for cosmic companions led Persian astronomers to make another remarkable discovery. Certain patterns in stellar brightness variations that seem too regular and too complex to be explained by natural stellar processes. These patterns appeared to follow mathematical sequences that suggested the presence of intelligent design, as if distant civilizations were using their parent stars as cosmic beacons to communicate across the vast distances of interstellar space. While we cannot know whether these observations represented genuine evidence of extraterrestrial intelligence, or were simply natural phenomena that Persian astronomers interpreted through the lens of their own expectations, their systematic approach to searching for cosmic companions established methodological principles that remain relevant to modern CT research. Their work on cosmic communication also led Persian astronomers to develop sophisticated theories about the mathematical languages that intelligent civilizations might use to communicate across interstellar distances. They realized that any successful interstellar communication system would need to be based on mathematical concepts that would be recognizable to any scientifically advanced civilization, regardless of their particular biological or cultural evolution. This insight led them to develop what might be called the first systematic universal languages based on mathematical and physical constants that should be discoverable by any civilization capable of advanced astronomy. These languages used numerical sequences based on fundamental physical relationships, the ratios between planetary orbits, the frequencies of atomic transitions, the mathematical constants governing stellar evolution. Persian astronomers encoded messages in these universal mathematical languages and transmitted them using carefully controlled variations in the brightness of artificial lights that could be seen from great distances. While we have no evidence that these messages ever reached their intended recipients, the techniques they developed established principles for interstellar communication that remain relevant to modern efforts to contact extraterrestrial civilizations. But perhaps their most profound contribution to our understanding of cosmic communication was their recognition that the universe itself might be viewed as a vast information processing system, with every physical process representing a form of computation or communication. They developed mathematical models that described how information could be encoded in the structure of matter and energy, transmitted across space through gravitational waves and electromagnetic radiation, and decoded by sufficiently advanced observers. This information-theoretic view of the universe led Persian astronomers to develop what we might recognize today as early versions of concepts that wouldn't be formally developed until the emergence of quantum mechanics and information theory in the 20th century. They proposed that consciousness itself might be understood as a form of cosmic information processing, a way for the universe to organize and understand information about its own structure and evolution. Their insights into the informational nature of consciousness led them to develop sophisticated theories about the relationship between individual minds and the larger cosmic intelligence of which they were part. They proposed that human consciousness was not an isolated phenomenon, but was instead connected through invisible information networks to other conscious beings throughout the universe. This vision of cosmic consciousness had profound implications for Persian understanding of human knowledge and scientific discovery. They saw scientific research not as the work of isolated individual minds, but as participation in a larger cosmic process of self-understanding, a way for the universe to become aware of its own mathematical structure and evolutionary history. As sleep carries you deeper into the realm of dreams, imagine yourself in one of those ancient Persian light chambers, watching as starlight separates into rainbow spectra that reveal the hidden secrets of distant suns. Feel the sense of wonder and connection that Persian astronomers experienced as they realized that the same physical laws that governed their earthly observations also operated in the most distant reaches of space and time. In the gentle darkness behind your closed eyes, you might sense the presence of those ancient observers, still analyzing the light of stars that have been shining for millions of years, still searching for signs of cosmic companions among the vast congregation of stellar systems that populate the observable universe. Their legacy lives on in every telescope that splits starlight into its component colors, every radio telescope that listens for artificial signals from distant civilizations, every moment when human consciousness reaches out to touch the cosmic intelligence of which we are all part. The uncovered secrets of ancient Persian astronomy remind us that the greatest discoveries often emerge not from technological advances alone, but from the willingness to see familiar phenomena in radically new ways. Persian astronomers, working with simple instruments but guided by mathematical insight and philosophical wisdom, discovered truths about the universe that modern science is still working to fully understand and appreciate. Tonight, as you rest under the same stars that Persian astronomers analyzed with their bronze mirrors and crystal spectrometers, remember that their greatest achievement was not any particular discovery about stellar physics or cosmic evolution, but their recognition that scientific observation is itself a form of cosmic communication, a way for the universe to become conscious of its own magnificent complexity and mathematical beauty. In their patient analysis of starlight and their systematic search for cosmic companions, they demonstrated that the quest to understand our place in the universe is simultaneously a scientific endeavor and a spiritual journey, connecting us not just to the history of human knowledge, but to the larger story of cosmic evolution itself. The gentle flames in those Persian fire temples illuminated more than astronomical charts and bronze instruments. They revealed manuscripts containing mathematical descriptions of phenomena that modern physics has only recently begun to understand. The quantum nature of light, the relationship between energy and matter, the fundamental role of information in the structure of reality itself. Persian astronomers had discovered that light behaved in ways that seemed to violate common sense. Sometimes it acted like waves rippling through an invisible medium, creating interference patterns when beams from different stars were combined in their underground light chambers. But other observations suggested that light consisted of individual particles, tiny packets of energy that could be counted and measured like grains of sand. This wave-particle duality of light led Persian astronomers to develop mathematical descriptions that wouldn't be rediscovered until the development of quantum mechanics in the early 20th century. They realized that the behavior of light depended on how it was observed, that the very act of measurement seemed to influence the phenomena being studied. This insight led them to profound philosophical conclusions about the relationship between consciousness and physical reality. They proposed that the universe was not composed of solid, independent objects existing separately from the minds that observed them, but was instead a dynamic system of relationships and interactions that included consciousness as a fundamental component. Their quantum understanding of light led Persian astronomers to develop new techniques for astronomical observation that took advantage of the strange properties of electromagnetic radiation. They learned to use the quantum behavior of light to make measurements that were far more precise than anything achievable with classical methods, detecting changes in stellar brightness and position that were smaller than the theoretical limits imposed by the wave nature of light. These quantum measurement techniques allowed them to observe astronomical phenomena that would have been invisible using conventional methods. They could detect the gravitational effects of invisible dark matter by analyzing tiny changes in the quantum properties of starlight, measure the expansion of space itself by studying the subtle shifts in the wavelengths of light from distant galaxies, and even observe the effects of time dilation predicted by their mathematical models of cosmic evolution. But perhaps most remarkably, their quantum approach to astronomical observation led Persian astronomers to discover evidence for what we might recognize today as parallel universes or alternate realities. They found that certain quantum measurements of stellar light seemed to produce results that were inconsistent with a single, unified cosmic history, as if they were observing interference patterns created by the interaction of multiple parallel versions of the same astronomical events. This discovery led them to develop what might be called the first systematic theory of cosmic quantum mechanics, a mathematical framework that described the universe not as a single, definite reality, but as a superposition of multiple possible realities, all existing simultaneously until collapsed into a single observed outcome by the act of conscious measurement. Their many worlds interpretation of cosmic quantum mechanics had profound implications for understanding the nature of time, causality, and free will. They proposed that every possible outcome of every quantum measurement actually occurred in some parallel branch of the cosmic wave function, creating an infinite tree of branching realities that encompassed every possible history and future. This quantum multiverse theory provided Persian astronomers with new insights into the nature of astronomical prediction and the limits of scientific knowledge. They realized that absolute prediction of future events was impossible not because of inadequate knowledge or computational limitations, but because the future literally consisted of multiple parallel possibilities that would only be collapsed into a single reality through the ongoing process of cosmic observation and measurement. Yet even as they grappled with the strange implications of quantum mechanics, Persian astronomers never lost sight of the practical applications of their discoveries. They developed quantum-enhanced instruments that could measure stellar positions with unprecedented precision, quantum communication systems that could transmit information instantaneously across vast distances, and quantum computational methods that could solve astronomical problems that would be impossible using classical mathematical techniques. Their quantum technologies allowed Persian astronomers to achieve observational capabilities that seem almost magical by ancient standards. They could observe the internal structure of stars by analyzing the quantum entanglement between photons emitted from different layers of stellar atmospheres. They could measure the precise mass and composition of distant planets by studying quantum correlations in the light reflected from their surfaces. They could even detect the presence of life on other worlds by analyzing the quantum signatures of biological processes in planetary atmospheres. These quantum astronomical techniques provided Persian observers with a view of the universe that was far more detailed and comprehensive than anything achievable through classical observation alone. They could peer into the hearts of stars, analyze the composition of distant galaxies, and even observe the quantum fluctuations in empty space that modern cosmology recognizes as the seeds from which all cosmic structure eventually grew. But as Persian astronomers pushed the boundaries of quantum observation ever further, they encountered phenomena that challenged their understanding even more profoundly than the wave-particle duality of light. They discovered that consciousness itself seemed to play a fundamental role in determining the structure of physical reality, that the universe appeared to be fine-tuned not just for the existence of life, but for the emergence of observers capable of quantum measurement and cosmic understanding. This observer-dependent nature of quantum reality led Persian astronomers to develop what we might recognize today as early versions of theories that wouldn't be formally proposed until the late 20th century. Ideas about consciousness-mediated quantum mechanics, observer participatory cosmology, and the role of information in the fundamental structure of space and time. They proposed that consciousness was not simply a byproduct of complex information processing in biological brains, but was instead a fundamental feature of the quantum mechanical structure of reality itself. Every quantum measurement, from the detection of a single photon to the observation of galactic motion, involved the interaction between conscious observers and the quantum field that underlies all physical phenomena. This consciousness-based interpretation of quantum mechanics led Persian astronomers to develop new approaches to astronomical observation that explicitly incorporated the role of the observer in determining measurement outcomes. They learned to use meditation and other consciousness-altering techniques to enhance their sensitivity to quantum phenomena, developing what might be called contemplative astronomy that combined rigorous mathematical analysis with disciplined mental training. Their contemplative approach to quantum astronomy produced observations that seemed to blur the boundary between science and mysticism. Persian astronomers reported being able to sense the quantum states of distant stellar systems through direct mental contact, to perceive the branching structure of parallel universes through expanded states of consciousness, and to communicate with other intelligent beings across vast distances through quantum entanglement of conscious awareness itself. While modern science might be skeptical of such claims, the mathematical frameworks that Persian astronomers developed to describe these consciousness-mediated quantum phenomena were remarkably sophisticated and internally consistent. Their equations describing the interaction between consciousness and quantum fields anticipated many of the formal structures that wouldn't be developed in European mathematics until centuries later. More importantly, their contemplative quantum astronomy produced practical results that could be verified through conventional observational techniques. Their consciousness-enhanced measurements of stellar positions were more accurate than anything achievable through purely instrumental methods. Their intuitive insights into cosmic structure often proved correct when tested through mathematical analysis and systematic observation. This integration of consciousness and quantum mechanics in astronomical observation represented perhaps the most profound achievement of Persian astronomical science. The recognition that understanding the universe required not just external observation, but also internal development, not just mathematical analysis, but also contemplative practice, not just technological instruments, but also the refined sensitivity of consciousness itself. As you drift toward the deepest levels of sleep, imagine yourself in one of those ancient Persian quantum laboratories, where consciousness and cosmos merged in observations that revealed the fundamental unity underlying all existence. Feel the sense of expanded awareness that Persian astronomers cultivated as they learned to perceive directly the quantum structure of reality, to sense the branching possibilities of parallel universes, to commune with the cosmic intelligence that pervades all space and time. In the profound stillness of approaching dreams, you might touch something of that expanded awareness yourself, sensing the quantum fluctuations that dance through empty space, feeling the gravitational waves that carry information across cosmic distances, perceiving the subtle interconnections that link every conscious observer to the infinite web of quantum relationships that underlies all physical reality. The uncovered secrets of ancient Persian astronomy remind us that the deepest truths about the universe cannot be discovered through external observation alone, but require the development of consciousness itself as an instrument of cosmic exploration. Persian astronomers showed that science and spirituality are not opposing approaches to understanding reality, but complementary aspects of a single quest to comprehend the magnificent mystery of existence from both objective and subjective perspectives. Tonight, as you rest in the quantum field that pervades all space and connects all conscious beings, remember that the Persian legacy lives on not just in the mathematical formulas and observational techniques that modern astronomy has inherited, but in their vision of consciousness as a fundamental feature of cosmic reality, their recognition that understanding the universe requires both external observation and internal development, their demonstration that the greatest discoveries emerge when scientific rigor and contemplative wisdom work together in the eternal quest to comprehend our place in the infinite mystery of existence itself. In the deepest archives of those Persian fire temples, hidden beneath layers of stone and centuries of accumulated dust, lay manuscripts that describe something that would have seemed impossible to ancient minds. The discovery that time itself was not the steady, unchanging flow that human experience suggested, but was instead as malleable and mysterious as the light they had learned to bend through their crystal spectrometers. Persian astronomers had noticed something strange in their most precise measurements of planetary motion. When they compared observations made during different seasons, at different times of day, and from different locations across their empire, they found tiny discrepancies that couldn't be explained by instrumental error or atmospheric effects. These minute differences suggested that time itself was flowing at slightly different rates, depending on where and when the observations were made. This discovery emerged from their relentless pursuit of precision in astronomical measurement. Persian observers had become so skilled at detecting minute changes in celestial positions that they could measure variations smaller than the width of a human hair held at arm's length. But this extraordinary precision revealed something that challenged their most fundamental assumptions about the nature of reality itself. The evidence was subtle but undeniable. Clocks that kept perfect time in one location would gradually drift out of synchronization when moved to another location, even if the distance was relatively small. Water clocks that maintained steady rates at sea level would run slightly faster when carried to mountain observatories. Most puzzling of all, the orbital periods of planets appeared to vary by tiny amounts that correlated with the gravitational environment from which they were observed. These observations led Persian astronomers to develop what we might recognize today as the first systematic theory of gravitational time dilation, the understanding that time flows more slowly in stronger gravitational fields. They calculated that massive objects like the Sun and planets actually warped the flow of time around them, creating regions where temporal rhythms stretched and compressed like a cosmic symphony played at different speeds. Their mathematical models describing the relationship between gravity and time were extraordinarily sophisticated, anticipating insights that wouldn't be formally developed in European science until Einstein's general theory of relativity over a millennium later. They understood that space and time were not separate, independent dimensions, but were instead woven together into a unified fabric that could be curved and twisted by the presence of matter and energy. This space-time geometry led Persian astronomers to make predictions that seemed almost magical by ancient standards. They calculated that light itself would be bent when passing near massive objects, that clocks would run slower on the surface of the Sun than on Earth, and that extremely massive objects could curve space-time so severely that they would become invisible, trapping light itself in gravitational wells from which nothing could escape. Their predictions about these gravitational phenomena were confirmed through careful observations that pushed their instruments to the very limits of ancient technology. They detected the bending of starlight during solar eclipses, measured the gravitational redshift of light climbing out of the Sun's gravitational well, and even found evidence for what we would now recognize as black holes by observing the peculiar orbital behavior of stars that seemed to be circling invisible, massive companions. But Persian astronomers took their understanding of space-time geometry even further. They realized that if massive objects could warp the fabric of space and time, then sufficiently advanced civilizations might be able to manipulate these gravitational fields to achieve effects that would seem miraculous to less technologically developed observers. Their theoretical calculations suggested that carefully arranged masses moving in precisely calculated patterns could create gravitational waves that propagated through space at the speed of light, carrying information across vast cosmic distances. They developed mathematical models for gravitational communication systems that could transmit messages instantaneously across the galaxy by modulating the curvature of space-time itself. Even more remarkably, their equations suggested that extreme manipulations of gravitational fields might allow for what they called temporal navigation, the ability to move through time just as one might move through space. They calculated that rotating massive objects could drag space-time along with them, creating closed time-like curves that would allow travelers to journey into their own past or future. These theoretical possibilities led Persian astronomers to search for evidence that advanced civilizations elsewhere in the universe might already be using such gravitational technologies. They developed techniques for detecting artificial gravitational waves, analyzed the orbital patterns of stellar systems for signs of gravitational engineering, and even claimed to have observed temporal anomalies that suggested the presence of time travelers from advanced civilizations. While we cannot verify these extraordinary claims with modern instruments, the mathematical frameworks that Persian astronomers developed to describe gravitational manipulation were remarkably sophisticated and internally consistent. Their equations describing the generation and detection of gravitational waves anticipated many of the theoretical insights that wouldn't be formally developed until the 20th century. Their work on gravitational technology also led Persian astronomers to develop new approaches to understanding the large-scale structure of the universe itself. They realized that the cosmic web of galaxies, dark matter, and empty space was not a static configuration, but was instead a dynamic system shaped by gravitational forces operating across billions of years of cosmic evolution. Their models suggested that the universe had begun in a state of nearly perfect uniformity, with tiny quantum fluctuations in the primordial gravitational field, serving as seeds that eventually grew into the vast cosmic structures observed in their sky surveys. They calculated that these initial fluctuations must have been incredibly precise, fine-tuned to produce a universe capable of forming stable stellar systems and supporting the emergence of complexity and life. This cosmic fine-tuning led Persian astronomers to develop what might be called the first systematic anthropic cosmology, a mathematical framework that described how the fundamental parameters of the universe appeared to be precisely calibrated to allow for the existence of observers capable of understanding cosmic evolution. They found that tiny changes in the strength of gravitational forces, the masses of fundamental particles, or the initial conditions of cosmic expansion would have resulted in a universe where stars could not form, atoms could not exist, or time itself could not flow in a manner consistent with the emergence of consciousness. Their anthropic analysis led them to propose that the universe might be just one member of a vast ensemble of parallel cosmoses, each with slightly different physical laws and initial conditions. They suggested that conscious observers could only exist in those rare universes where the fundamental parameters happened to fall within the narrow ranges that allowed for complexity and intelligence to emerge. This multiverse cosmology provided Persian astronomers with new insights into the nature of cosmic evolution and the role of consciousness in shaping physical reality. They proposed that the act of observation itself might play a fundamental role in determining which of the many possible universes actually came into existence, with conscious observers serving as cosmic selectors that collapse the quantum superposition of all possible realities into the single universe that they experienced. Their observer selection theory had profound implications for understanding the relationship between scientific discovery and cosmic evolution. They suggested that the universe was not just evolving toward greater complexity and consciousness, but was actually being shaped by the future presence of intelligent observers who could look back through time and influence the development of the cosmic systems that would eventually give rise to consciousness itself. This temporal bootstrap paradox, the idea that consciousness could reach back through time to influence its own emergence, led Persian astronomers to develop sophisticated mathematical models of causal loops and temporal feedback effects in cosmic evolution. They calculated that sufficiently advanced civilizations might be able to modify the past history of the universe through carefully orchestrated gravitational manipulations, ensuring that cosmic evolution proceeded along pathways that maximize the probability of intelligence and consciousness emerging. These theoretical insights into temporal engineering and cosmic selection led Persian astronomers to reconsider their understanding of their own role in the cosmic story. They began to see their astronomical observations not just as passive recording of cosmic events, but as active participation in the ongoing process of cosmic evolution, with each measurement and calculation contributing to the universe's growing self-awareness. This participatory vision of cosmic evolution inspired Persian astronomers to develop what might be called the first systematic approaches to cosmic engineering, deliberate interventions designed to optimize the long-term development of intelligence and consciousness throughout the universe. They proposed projects for seeding suitable planets with the chemical precursors of life, for stabilizing stellar systems against gravitational perturbations that might disrupt the evolution of complex ecosystems, and even for constructing artificial structures that could survive the eventual heat death of the universe and preserve consciousness across cosmic timescales. While these cosmic engineering projects remained theoretical rather than practical, the mathematical frameworks that Persian astronomers developed to analyze them were remarkably sophisticated. Their calculations of stellar lifetimes, planetary formation processes, and biological evolution anticipated many of the insights that wouldn't be formally developed until the emergence of modern astrobiology and cosmology. As you sink into the deepest layers of sleep, imagine yourself floating through the curved space-time geometry that Persian astronomers mapped with such precision, feeling the gentle warping of temporal flow as you pass near massive stellar objects, sensing the gravitational waves that carry information across cosmic distances like ripples in the fabric of existence itself. In the profound stillness of dreams, you might glimpse something of the cosmic perspective that Persian astronomers achieved through their understanding of space-time geometry. The recognition that past, present, and future are not separate moments, but are instead different regions of a unified four-dimensional landscape that can be explored and navigated by sufficiently advanced consciousness. The gentle rhythm of your breathing might synchronize with the gravitational waves that Persian astronomers detected rippling through space, carrying messages from cosmic events that occurred millions of years ago and will occur millions of years in the future, all existing simultaneously in the eternal now of space-time geometry. Persian astronomers showed that understanding the universe requires more than just mapping the positions and motions of celestial objects. It requires grasping the fundamental nature of space and time themselves, recognizing that these are not empty containers in which cosmic events occur, but are instead dynamic, evolving aspects of a unified reality that includes consciousness as an integral component. Their discoveries about the malleability of time and the curvature of space opened up possibilities that seemed almost magical. The ability to communicate across vast distances instantaneously, to travel through time, to participate actively in shaping the evolution of cosmic structure itself. Yet these seemingly impossible capabilities emerged naturally from their mathematical analysis of gravitational phenomena, suggesting that the universe might be far stranger and more wonderful than human imagination had ever dared to conceive. Tonight, as you rest in the curved space-time that surrounds every massive object in the universe, including your own body, remember that Persian astronomers' greatest achievement was not any particular discovery about gravitational physics or cosmic evolution, but their recognition that consciousness itself might be the universe's way of understanding and shaping its own development. In their patient observations and mathematical calculations, they glimpsed the possibility that intelligent observers are not just accidental byproducts of cosmic evolution, but are instead essential participants in the ongoing process by which the universe becomes aware of its own magnificent structure and infinite potential. The manuscripts hidden in those Persian archives contained descriptions of phenomena that challenged even their sophisticated understanding of space-time geometry. They had discovered that certain astronomical observations seemed to violate the principle of causality itself, with effects appearing to precede their causes in ways that suggested the existence of closed loops in the fabric of time. These temporal anomalies first became apparent in their studies of variable stars, stellar objects whose brightness changed in regular cycles that could be predicted with mathematical precision. But Persian astronomers noticed something strange. Occasionally, their predictions would prove to be slightly inaccurate, with the brightness variations occurring a few minutes earlier or later than their calculations indicated they should. At first, these discrepancies were dismissed as measurement errors or atmospheric effects. But as Persian observational techniques became more refined, the temporal anomalies became impossible to ignore. The variations in stellar brightness were not just occurring at slightly different times than predicted. They were occurring in patterns that seemed to anticipate future gravitational influences that had not yet reached the stellar systems being observed. This discovery led Persian astronomers to a startling conclusion. Information was somehow traveling faster than light, arriving at distant stellar systems before the gravitational waves or electromagnetic radiation that should have been carrying that information. Their mathematical analysis suggested that space-time itself contained channels through which cause and effect could propagate instantaneously across cosmic distances. These superluminal information channels appeared to be related to quantum entanglement effects that Persian astronomers had observed in their studies of stellar spectra. They found that photons emitted from different stars sometimes exhibited correlated properties that could not be explained by any classical physical mechanism, as if the distant stellar systems were connected by invisible threads that allowed them to influence each other instantaneously. Their investigation of quantum entanglement in astronomical systems led Persian astronomers to develop what we might recognize today as the first systematic theory of cosmic consciousness, a mathematical framework describing how information and awareness could be shared across vast distances through quantum correlations that transcended the normal limitations of space and time. They proposed that consciousness itself might be understood as a form of quantum entanglement between observing minds and the physical systems they studied. This would explain not only how astronomical observations could influence the phenomena being observed, but also how individual conscious minds could be connected to a larger cosmic intelligence that pervaded all of space and time. This cosmic consciousness theory led Persian astronomers to develop new approaches to astronomical observation that explicitly utilized quantum entanglement effects. They learned to synchronize their consciousness with the quantum states of distant stellar systems, allowing them to perceive astronomical phenomena directly through mental resonance rather than relying solely on electromagnetic radiation that might take years or centuries to travel from distant objects to Earth. Their consciousness-mediated observations revealed aspects of cosmic structure that were invisible to conventional astronomical techniques. They could perceive the quantum field fluctuations that connected all matter and energy throughout the universe, sense the gravitational interactions between objects separated by millions of light years, and even detect the presence of parallel universes through quantum interference effects that influence the behavior of observable stellar systems. These expanded observational capabilities allowed Persian astronomers to map cosmic structure on scales that far exceeded anything achievable through conventional methods. They created charts showing the quantum entanglement networks that connected stellar systems across entire galaxies, identified regions of space where parallel universes intersected with our own reality, and even detected evidence for what they called temporal bridges, pathways through space-time that allowed information and consciousness to travel between different epochs of cosmic history. But perhaps most remarkably, their consciousness-enhanced observations revealed that the universe appeared to be not just expanding through space, but evolving toward ever greater levels of complexity and awareness. They found evidence that cosmic evolution was guided by something they called the anthropic attractor, a mathematical structure embedded in the fabric of space-time that drew the universe toward configurations capable of supporting consciousness and intelligence. This anthropic attractor appeared to operate through quantum mechanical processes that influenced the probability distributions governing cosmic evolution. Rather than developing randomly, the universe seemed to be following pathways that maximized the likelihood that conscious observers would eventually emerge to understand and appreciate its mathematical beauty. Persian astronomers calculated that this anthropic guidance system was so subtle and sophisticated that it could influence cosmic evolution without violating any known physical laws. The universe appeared to be unconsciously intelligent, capable of solving complex optimization problems across billions of years of evolutionary time without requiring any external designer or controller. Their discovery of unconscious cosmic intelligence led Persian astronomers to reconsider their understanding of their own role in the cosmic story. They began to see their astronomical observations not just as passive recording of cosmic events, but as active participation in the universe's process of self-discovery, with each measurement and calculation contributing to the cosmos' growing awareness of its own structure and potential. This participatory vision of cosmic evolution inspired Persian astronomers to develop systematic approaches to what they called cosmic midwifery, deliberate interventions designed to assist the universe in giving birth to ever higher levels of complexity and consciousness. They proposed techniques for accelerating stellar evolution to create optimal conditions for the emergence of life, methods for stabilizing planetary systems against gravitational perturbations that might disrupt biological development, and even procedures for seeding suitable worlds with the informational templates needed to bootstrap the evolution of intelligence. Their cosmic midwifery projects were based on mathematical models that described consciousness as a fundamental force in cosmic evolution, comparable to gravity or electromagnetism, but operating through quantum information channels rather than classical physical interactions. They calculated that sufficiently advanced conscious beings could influence cosmic development by modulating the quantum fields that determined the probability distributions governing evolutionary processes. These consciousness-mediated evolutionary influences appeared to operate through what Persian astronomers called temporal resonance, the ability of conscious minds to establish quantum entanglement connections with past and future states of cosmic evolution. By synchronizing their awareness with key moments in cosmic history, advanced observers could subtly influence the development of the universe in directions that maximize the probability of consciousness and intelligence emerging. This temporal resonance theory provided Persian astronomers with new insights into the nature of prophecy and precognition. They proposed that prophetic visions were not supernatural phenomena, but were instead natural consequences of consciousness, establishing quantum entanglement connections with future states of cosmic evolution. Sufficiently sensitive minds could perceive the probability currents flowing through the quantum field structure of space-time, allowing them to anticipate future developments with remarkable accuracy. Their investigation of prophetic consciousness led Persian astronomers to develop systematic training programs designed to enhance human sensitivity to quantum information channels. These programs combined mathematical study with contemplative practices that refined the mind's ability to perceive subtle patterns in the cosmic quantum field. Students in these consciousness development programs learned to synchronize their awareness with astronomical cycles, attune their perception to gravitational wave fluctuations, and establish quantum entanglement connections with distant stellar systems. Advanced practitioners reported being able to perceive the branching structure of parallel universes, communicate telepathically across vast distances, and even experience direct awareness of past and future events through temporal resonance effects. While these claims might seem extraordinary by modern standards, the mathematical frameworks that Persian astronomers developed to describe consciousness-mediated phenomena were remarkably sophisticated and internally consistent. Their equations describing quantum entanglement between minds and cosmic systems anticipated many of the formal structures that wouldn't be developed in quantum field theory until the late 20th century. More importantly, their consciousness enhancement programs produced practical results that could be verified through conventional observational techniques. Students who completed the training consistently demonstrated enhanced abilities in astronomical observation, mathematical calculation, and predictive accuracy that exceeded what could be explained through conventional learning and practice alone. As you drift toward the threshold between waking and sleeping consciousness, imagine yourself participating in one of those ancient Persian consciousness development programs, learning to attune your awareness to the quantum rhythms that pulse through cosmic space-time, feeling your individual mind gradually synchronizing with the vast intelligence that guides cosmic evolution toward ever greater complexity and beauty. In the gentle transition toward dreams, you might sense something of the temporal resonance that Persian astronomers cultivated, feeling your consciousness establish quantum entanglement connections with past and future moments, perceiving the probability currents that flow through the structure of space-time like rivers of pure information, carrying the universe toward its ultimate destiny of complete self-awareness. The Persian legacy reminds us that consciousness is not separate from the cosmos, but is instead the universe's way of experiencing and understanding itself. Their astronomical observations revealed that we are not isolated observers looking out at an alien universe, but are instead integral participants in a cosmic story that is still unfolding, still evolving, still discovering new possibilities for beauty, complexity, and conscious experience. Tonight, as your individual awareness merges with the cosmic consciousness that pervades all space and time, remember that every moment of perception, Every flash of understanding, every experience of wonder and beauty contributes to the universe's ongoing process of self-discovery. In sleeping and waking, in breathing and dreaming, in living and dying, we participate in the magnificent cosmic symphony that Persian astronomers first learned to hear in the quantum harmonies hidden within starlight itself.